Hello everyone, my name is Gary O'Mealy, and in this video we are going to introduce ourselves to some of the basic pharmacology that deals with the interactions between ligands and receptors. So the science of pharmacology, which you may have heard of before, you may not have heard of before, you may have heard the word before and maybe not know exactly what it means. Basically, pharmacology concerns itself with the interactions between ligands and receptors in living systems. Now, the classical definition of pharmacology usually comes to mean pharmaceutical drugs, but some of the principles we're going to learn about here are very useful in talking about natural ligands as well. So, what we know from our previous lessons is that a biological response is going to be dictated by how much ligand is present and how many receptors are available. So we've learned, obviously, the fundamental principle that the only way to activate a cell's signal transduction pathway is to get a ligand to bind to a receptor. So it's only natural that we should expect that having lots of ligand and having lots of receptors should maximize the ability for us to activate a response. Now, I say having lots of ligand, but in reality, that's not usually going to be the case. In most cases, a lot of extracellular ligands, including hormones and neurotransmitters, are only secreted in very, very, very low concentrations. In terms of concentration, we're only talking as much as nanomolar concentration, that's 10 to the minus 9th, and as low as picomolar concentration, that's 10 to the minus 12th. So those are exceedingly small concentrations of hormone or neurotransmitter, such low concentrations that it makes you wonder how we actually ever get ligand to bind a receptor. Okay, so far what we've established is that all the ligands that we've been talking about in our previous lessons are secreted in very, very, very low quantities. So how do we get around that? Well, for that reason, the fact that we do secrete these molecules in such low amounts, it's going to be very important that the receptors have high affinities for their ligands, meaning that the receptors really, really, really bind to those ligands very, very tightly and with high specificity. Okay, so to delve a little bit further into this topic, first let's consider basically consider the idea that a receptor can do one of two different things at any given time. It has two potential states. Either the ligand is bound or the ligand is not bound. Seems easy enough, right? Well, what we know is that if we want a signal transduction process to be active to produce a biological response, the ligand needs to be in a bound state. Otherwise, if the ligand is not bound, then the process is not going to happen, okay? So whether the ligand actually is bound or not is going to be determined by three factors. Number one, how many available receptors are located on or in the target cell. We've obviously talked about the idea that non-target cells do not have receptors for a particular ligand, so in that case there's nothing else to really talk about. If a cell does not have any receptors at all, it is not going to produce a response. From there, it's a little bit of a sliding scale. If a cell only has a few receptors, it's going to be limited in terms of how strong of a response it can produce. And if a cell has a lot of receptors, it has the potential to produce a very strong response, depending on how much ligand is present. Speaking of which, the extracellular fluid concentration of the ligand is highly relevant, and we have already established that we can usually expect this concentration to be fairly low. But the thing that helps us get around that is the concept of receptor affinity that we mentioned on the previous slide. So let's go out of order here and talk about receptor affinity first. So what we can think about for a receptor is that this is very much like a reversible chemical reaction. The receptor starts in an unbound state, and once we make ligand available, we go to the bound state in which the receptor and the ligand come together to produce a response. The ligand and the receptor will come together at a given rate, which we will call the on rate. Similarly, once the ligand is bound to the receptor, the ligand can, of course, become unbound. It can come off of the receptor and force the receptor back into an unbound state. This process will occur at what we call the off rate. Now, measuring a receptor's affinity for its ligand is actually mathematically very easy. Receptor affinity is measured by the ratio of the off rate to the on rate. We call this the dissociation constant for the receptor, or the KD value. You can see, again, this is just a ratio of the off rate to the on rate. Okay? So the idea here is that if the receptor does have a very high affinity for its ligand, this KD ratio should be a very, very, very small number. If the affinity is high, that would indicate that the on rate is a very large number and the off rate is a very small number. And since the small number is in the numerator and the big number is in the denominator, that would make the absolute value of the KD be a very, very, very small number indeed. The vice versa is true as well. If the receptor has extremely poor affinity for its ligand, then the KD value would be a very big number. The off rate would be very large and the on rate would be very low. So if a receptor has a low affinity, that would indicate the receptor spends more time in the unbound configuration than it does in the bound configuration. So what you can see here are some approximate KD values for some binding proteins that are going to be relevant for us. Now, the receptor avidin, which is a protein, and its ligand biotin, which is a B vitamin, the reason why I'm showing you this is not because it's super relevant for human physiology, but because the interaction between avidin and biotin is the strongest known biological interaction that we know of, with a KD value of 1.3 times 10 to the negative 15th molar. Another way of thinking about this is that if you had a certain number of avidin molecules and biotin existed at a concentration of 1.3 times 10 to the negative 15th molar, which is a ridiculously low concentration, half of those avidin molecules would be bound to biotin. So that is the strongest known biological interaction that we know of. And the reason I'm showing you this is to kind of give you some context, give you a basis of comparison, so you can understand kind of what the affinity of more relevant receptors and ligands looks like for us. So if you compare that to the insulin receptor has an affinity for insulin that is approximately 4 times 10 to the negative 10th molar. That is still a very, very, very high affinity, but that affinity is somewhere in the neighborhood of 10 to 100,000 times weaker than the affinity avidin has for biotin. It's still really strong, but that really just gives you a sense for how strong an affinity avidin has for biotin. Just as kind of an aside, avidin is a big reason why you should not eat raw eggs. Avidin is a protein that, among other places, is found in raw eggs. Cooking eggs actually destroys avidin through the denaturation process that we've talked about before, but if someone were to eat raw eggs, that avidin would maintain its folded shape, it would get into your digestive system, and any biotin, which again is one of the B vitamins that we need, any biotin that you get from the diet would get leached up by that avidin and would not get absorbed into your system. So that's one of many reasons why you should not ever eat raw eggs, because then you wouldn't get those biotin nutrients that you need. Okay, so just out of general interest, another way of expressing the KD value is in the numerator, the concentration of ligand times the concentration of free receptor divided by the concentration of the ligand receptor complex. So LR, you can think of the number of occupied receptors. L would be equal to the amount of free ligand in the extracellular fluid, and R would be equal to the number of empty receptors in the unbound state. So again, the idea here is that if a receptor has very high affinity for its substrate, for its ligand, then we should have a lot more receptors bound to the ligand than we should have receptors that have nothing to do, as long as the ligand is present. But what we have seen and will continue to see is that ligands like hormones and neurotransmitters are only secreted in very specific circumstances. So there will be a lot of times in which the concentration of ligand is practically zero, and even with a high affinity, a receptor would not be bound because, hell, the ligand is not there. Okay, so one more thing, another way of thinking about a receptor's KD value mathematically is that the KD is equal to the ligand concentration at which half of the available receptors will be bound. Since a strong KD value is a very small number, that means that we can get receptors effectively bound with ligand even when the ligand concentration is very, very, very low. So if we back up for just a moment to this statement right here, where we said most extracellular ligands are secreted in very, very low concentration between 10 to the minus 9 and 10 to the minus 12th. Well, if we go ahead and compare to, say, the KD for the insulin receptor, which has a KD of 4.2 times 10 to the minus 10th, that's right in that 10 to the minus 9th, 10 to the minus 12th range. So what that's indicating to you is that it's a good thing that the insulin receptor has such a strong affinity. We can get insulin to bind to its receptor even when the insulin concentration in the serum is very, very, very low. That is what we mean by the importance of receptor affinity. We can still get potent biological responses even when the ligand concentration is very low. Okay. So, bottom line here, if a receptor has high affinity for its ligand, then a small amount of ligand should cause most of the available receptors to be occupied and therefore activated. Okay, so let's talk about a couple of other things. Modulating responses. So we know that if the ligand concentration is high enough and if there are available receptors, we should activate those receptors and we should produce a response. But we're going to see here that there are going to be times, even when the ligand is available, that we do not want the response to happen. Okay, say for example, that your blood sugar starts to get kind of high, your pancreas will start releasing insulin into the bloodstream. Insulin will bind to insulin receptors on target cells, and that will start to lead to the blood glucose coming back down. Well, once the blood glucose goes back to normal, we don't need the insulin anymore. We don't need to activate those insulin receptors anymore. But the deal here that makes hormonal negative feedback a little bit different is that even once the stimulus has gone away, as long as there are hormones available and receptors available, that response will stay on. So the cell is going to have to get a little bit creative in order to turn these hormonal responses off. Okay? So first, let's talk about the fact that all ligands, including hormones and neurotransmitters, have half-lives. A half-life refers to the amount of time for the concentration of a molecule in the body to drop by 50%. So, some things that contribute to this half-life, in the case of neurotransmitters are destroyed by enzymes that are in the synapse, meaning that after a neurotransmitter has activated its receptors, after a certain amount of time, that neurotransmitter's naturally going to go away because there's an enzyme right there in the synapse that is going to destroy it. Hormones, on the other hand, which are traveling through the bloodstream, are going to either be degraded or inactivated by their target tissues or by the liver or the kidneys, or there's going to be some mechanism for making sure that hormones over time start disappearing from the bloodstream. So most hormones, as luck would have it, have half-lives that are in the range of a couple of hours. So once your body deposits a hormone into the bloodstream, we can count on that hormone being present in the bloodstream at least for several hours. So consider this case here, where we have a hormone illustrated by green dots that is present in the bloodstream, and we're going to say that it has a half-life of 4 hours. What this means is that if you count up the number of molecules that are present here, we have 20 hormones that are visible in the bloodstream. But if we wait another 4 hours, the number of available hormones should decrease by half, meaning now there should only be 10 hormones present. If we wait another 4 hours, 10 should go down to 5. Theoretically, if we wait another 4 hours, that should go down to 2 or 3. I say 2 or 3 and not 2.5 because it's not possible to have half of a molecule, but you get the idea. Every time you wait the amount of time that is dictated by the half-life, the current concentration will go down by half. So theoretically, the concentration would never actually hit 0. It would approach 0, but not actually get there. But this is just the natural process by which the concentration of a hormone or neurotransmitter decreases over time. So the bottom line here is that once a stimulus has been removed, and hormone or neurotransmitter is no longer being secreted, such that the only available hormone or neurotransmitter that is currently available are those that had been previously secreted when the stimulus was still present, those hormones or neurotransmitters will naturally start disappearing over time, and as the extracellular concentration of ligand goes down and down and down over time, we can expect the response that is being generated by cells with these receptors to get weaker and weaker and weaker as more and more and more receptors go from a bound state to an unbound state, because that L concentration gets lower and lower and lower. Okay, and then the last way that we're going to talk about that a cell can regulate how strong a response is by adjusting the number of available receptors at the cell membrane. So the cell will typically do this for one of two reasons. Either, number one, because there is an excessive amount of ligand present and the cell doesn't want to keep the response on for too long, or number two, the opposite scenario, there is no ligand present and the cell wants the response to get turned on. So let's talk about receptor downregulation first. Here we are imagining a scenario in which there is way too much ligand available in the extracellular fluid. This is typically seen in cases of someone being on a pharmaceutical drug, such as a painkiller. If someone is on a painkiller for a long time and they take it several times a day, cells with opioid receptors are going to be constantly bombarded by ligand in the extracellular fluid, and the pain-killing properties of the receptor is going to be turned on pretty much all the time. Well, the cell in the body has a natural defense mechanism against this because it is not the natural order of things to want to keep biological responses on all the time. So one thing we could do is wait for the concentration of ligand to naturally diminish based on what we talked about with half-life. But again, if this is a pharmaceutical drug that someone is taking, the ligand is just going to be replenished the next time they take a pill. So the cell's other option to turn the response off, since we can't do anything about the ligand, is to actually remove the receptor. If this cell no longer has receptors for the ligand, then we cannot produce a response, no matter how much ligand is present there in the extracellular fluid. So again, this is called receptor downregulation. What happens here is that the receptor bound to the ligand is internalized into the cell by endocytosis. The ligand and the receptor together are inserted into an endocytic vesicle, which is now inside the cell, and this vesicle is eventually going to fuse with the lysosome, which is a hydrolytic organelle that contains a lot of enzymes that are going to be able to destroy the receptor and destroy the ligand. So if the receptor is destroyed and is no longer present in the plasma membrane, then we can no longer get a response, and therefore, no matter how much ligand is present in the extracellular fluid, we will not get a response as long as these receptors have been downregulated. Okay, well, let's talk about the opposite scenario. Imagine that a receptor is unbound because there is no ligand present. Well, in these cases, the cell does what we like to call priming itself. The cell basically has a way of recognizing that, okay, it's not time for us to activate this response yet because there is no ligand present, but let's go ahead and get things set up so that when ligand does become available, we're going to be ready to produce a really strong response. And the way the cell does this is by synthesizing new receptors via transcription and translation. Keep in mind, every receptor that your cells make is coded in the DNA. So through transcription and translation, we can make more copies of these receptors so that by the time ligand does become available, there are going to be a lot more receptors that are available to bind to the ligand, and with more receptors activated, the response will be all the stronger, okay? So now that we've talked about receptor up and down regulation, let's talk about how the endocrine system strategically deals with these processes to maximize the effectiveness of hormonal cell-to-cell communication. So in order for the cell or the body to take advantage of receptor upregulation while avoiding receptor downregulation, a lot of endocrine glands engage in what is called pulsatile secretion of their hormones. What this means is that instead of secreting their hormones as kind of a linear gradient, in other words, just kind of outputting a steady stream of hormone over time, instead of doing that, the endocrine gland will secrete a big burst of hormone in a short amount of time and then just stop. And then it'll secrete a big burst again a little while later, and then it stops. And it just keeps doing this over and over and over again. And what this does is this strong burst of hormone takes advantage of the receptor upregulation so that we get all those receptors bound. But before the cell has a chance to downregulate those receptors, the ligand is already gone because the endocrine gland has already stopped secreting. Okay, so we avoid receptor downregulation in that way. Then by the time the next burst occurs, we can still produce a very strong response. If you want to see what this looks like graphically, on the y-axis here, you can see the serum concentration of a particular hormone, and on the x-axis, you can see time in hours. So what you're seeing here are these big bursts of hormone secretion that I've been mentioning. So by the time the stimulus presents itself, we secrete a large amount of hormone into the bloodstream over a short amount of time. Once this hormone gets to high concentrations, that will activate the receptors and activate the responses. But before the downregulation can occur, you can see the concentration of the ligand goes way, way, way back down so that receptor downregulation does not prove necessary. And by the time we secrete another big burst of hormone, those receptors that can bind to the hormone are still available. Okay, that's going to do it for this video. Here is a list of vocabulary terms you might want to be aware of. And for checking your understanding, number 1, are hormones and neurotransmitters secreted in very high concentrations? And if not, how does receptor affinity play into this? Number 2, how is receptor affinity for a ligand measured? In other words, what metric do we use to measure that? And finally, how does a cell regulate its own sensitivity to a ligand? Okay, that's going to do it for this video. If you have any questions, go ahead and drop them in the comments section. Otherwise, I will see you for the next video.